write this next section in Unit 3 is 3.2. I can understand and perform matrix arithmetic. So let's write the word arithmetic. Arithmetic. All right, so we're going to be doing a little bit of math with these matrices here, but the warm-up here says match each property of addition with its example. Now these are just regular old addition properties. So this one says the commutative property. Remember, when you commute, you move from one place to another. So what we're looking for is we're looking for an addition problem where things have moved around. So this one doesn't look like anything's moved around. This one right here, take a look. A plus B is equal to B plus A. That is definitely the commutative property. We've moved the A and B around in an addition problem, and that's what it means to have the commutative property applied. The next one is the associative property. When you associate with things, you group them. So we're looking for things that have changed their grouping. So grouping normally requires parentheses, and the only two with parentheses are these guys right here. And this is the one that's changed the grouping. Here A and B were grouped, and here B and C are grouped. So the associative property of addition is illustrated right there. Now the additive identity, remember, identity means when we add something, it gets to maintain its identity. It gets to stay the same. So the number that we add to keep a number the same is 0. So that's going to be this one right here, which of course means this has got to be the additive inverse property. Remember, inverse means they cancel each other out or they undo each other. So I've got an A and I've got a negative A. They cancel each other out. They make a 0. Okay? Now, does the commutative property work with subtraction? So in other words, if I had A minus B, would that be the same as B minus A? And the answer to that is no. And you can come up with a numeric example really quickly. If we did 10 minus 3, would that be the same as 3 minus 10? Here we'd get a 7, and here we'd get a negative 7. So it does not work with that. Now, we can do arithmetic with matrices just like we can with regular numbers, but we've got to pay attention to some things, because just like with regular numbers, there are times when there are things that we can do with addition and multiplication that we cannot do with subtraction, like the commutative property, or division. So keep in mind there are problems with division also, like dividing by 0. So we've got to be much more careful with subtraction and division than we do with addition and multiplication. So matrix arithmetic is pretty easy. We've just got to remember a couple of rules, and we've got to keep things organized. So let's take a look at matrix addition and subtraction by the same token. So the first thing that we want to check for is they've got to have the same dimensions. So let's write down dimensions here. This is why we were talking about last time that it's so important. You've got to be able to figure out the dimensions. They've got to have the same dimensions. And then we add or subtract element by element. We go through each one of the positions, and we either add those positions together or we subtract them. And the dimensions of the resultant matrix is the same as the two original matrices. So if they had the same dimensions to begin with, they keep those same dimensions in the end result. And the word resultant is just a fancy word for the result, okay, of a mathematical operation. So if you hear somebody say resultant, it's just a fancy word for result. So let's take a look at example 1. It says add or subtract. If the operation is not possible, write not possible and then say why it's not possible. So on this one right here, the first thing we want to check is they've got to have the same dimensions. So this has 1, 2 rows, 1, 2, 3 columns. So that's a 2 by 3. And then this one right here has 2 rows and 1, 2 columns. So we can stop right there. So we're going to write not possible. It is not possible to add those together. And the reason is not same dimension. Now I'm just going to write DIM for dimension from now on. Let's take a look at this next one here. On this one we have 2 rows and 2 columns. And we get pretty good at recognizing the dimensions, hopefully. So this is a 2 by 2, and that's a 2 by 2. So the resultant is going to be a 2 by 2. So what we can do here is we can say, well, we're going to take this one right here, first row, first column, and we're going to subtract whatever's in the first row, first column. So this is going to be 1 minus 6. So that's going to be plus 6. So that's going to be a 7. This is going to be a 2 minus a 3. So that's going to be a negative 1. This is going to be a negative 4 minus a 4, so that's going to be negative 8. And this is going to be 5 minus a 10, so that's going to be negative 5. That right there is the answer. There is one thing that you could do with this, and this is why there's an asterisk here. We could distribute this through and kind of think of this as a minus and just put a plus right here. So this is going to be a plus. that would be a minus, that would be a minus, and that would be a minus. So it's kind of like distributing there. And then you'll notice that we go through and we've got a 1 and a 6, that's a 7, a 2 and a negative 3, that's a negative 1, a negative 4 and a negative 4, that would be a negative 8. So it is possible to change a subtraction problem into an addition problem. So it's really a question of which one you like here. And then on this one here, again, we're going to check the row and the column. So this is going to be a 2 row, 2 column, so 2 by 2 here. This is a 2 by 2, so the end result is going to be a 2 by 2. Sometimes I like doing this, just putting kind of a little line there to remind me, oh, I've got 4 little entries that I need to find. So this is going to be 6 minus 1, so that's going to be negative 7. And this is going to be 3 minus 2, so that's going to be 1. This is going to be 4 minus a minus 4, so that's a plus 4, so that's going to be an 8. And then this is a 10 minus a 5, so that's going to be a 5 right there. Now, I'm going to make this really clear what the answer is, negative 7,185. We're going to circle that. There's the answer, and we're all set to go. I do want to point out why this has an asterisk, though. You'll notice that this one right here, this is this matrix right here. So what I did here is this is a subtraction problem, and I reversed the order of these, so I switched them around. So you'll notice I could still get an answer, but the answer is not the same. So the commutative property of subtraction, there isn't one. Okay, it does not work. So addition is commutative, subtraction is not. So please don't do that. Just like with regular numbers, you can't switch those around. That's why we did this example up here to kind of point that out, that the commutative of, there is no commutative property of subtraction. Okay, so let's take a look down here. It just says add or subtract. If the operation is not possible, write not possible and state why. So the same type of thing as we just got done doing up above. So let's go ahead and take a look at this. It says we've got this 2 by 2 and we've got this 2 by 2. So we're going to have a 2 by 2. And a lot of times I like making them nice and big because I have a hard time writing as small as that font is. So we're going to do 1 plus a negative 6. That's going to be a negative 5. 2 plus the 0, so that's going to be a 2. 4 plus a 3, so you kind of see how we're doing this element by element. 5 plus the 4, so that's going to be a 9. We go ahead and circle that one. This is a 2 by 2, and to keep this easy, I've kept the dimensions fairly small. That's also a 2 by 2. So I'm going to go through and I'm going to do this. I'm going to distribute that negative through there, so I'm going to make this a minus. That's going to be a plus. That's going to be a plus, and that's going to be a minus. So let's see what we've got here. We've got a 1 and a negative 6, so that's a negative 5. A 2 and an 8, that's going to be a 10. A 4 and a 1, remember that's a positive 1, so this is going to be a 5. And then we've got a 5 minus a 2, so that's going to be a 3. So we're going to go ahead and circle that, and we are all set. Next one, I'm going to write this up. Well, I guess I've got room. This is a 2 by 2. This is a 2 by 2. This right here is the 0 matrix. Remember, that's the 0 matrix. So when we can definitely add those together, we're going to get a 2 by 2. So 0 plus 1 is 1. 0 plus 2 is 2. 0 plus 4 is 4. So you'll notice what happened here. This didn't change at all. So the 0 matrix is the additive identity. It doesn't change that matrix at all. As long as you can add those together, it's not going to change it at all. Now, when we're dealing with matrices, we need a way of telling a difference between a regular number and a number that's inside a matrix, or a number that's an entry in a matrix. So we already know that we can call an entry in a matrix an element. So the numbers inside the matrix, those are called elements or entries here. So what we do is we call a plain old number that's not in a matrix, we call it a scalar. So that's how you spell scalar. So a scalar is just a plain old number that's not inside a matrix. So if we look at this example right here, it says which 5 is a scalar and which one is an element. Well, this 5 right here is an element. That's inside a matrix. This 5 right here is not inside a matrix, so that one is just a scalar. So a scalar is the word that we use for a plain old number when we're dealing with matrices. So let's flip the page over and take a look at these, and let's talk about scalar multiplication. Scalar multiplication is pretty cool because it's very easy. It works a lot like distributing. All we do is we multiply element by element. It's just like distributing. So here's what I mean when I talk about that. If we're going to multiply this 3 on the outside, this scalar with this matrix, what we do is we basically distribute that 3 through to all of those. So this is a 2 by 2. It doesn't change the dimensions at all. All it does is make each one of those 3 times bigger than they used to be. So 3 times 1 is 3, 3 times 2 is 6, 3 times 4 is 12, and 3 times 5 is 15. That's it. That's all we do. We take that scalar on the outside and we multiply each one of those elements. Element by element, we go through the matrix and we multiply there. Now, on example B, it's got matrix A and matrix B. You'll notice that they are both 2 by 2s. That's important. And it wants us to find 4 times A plus 2 times B. So here's what we need to do. We need to multiply a 4 into each one of these, and we need to multiply a 2 into each one of these. So we're going to write down what we get here. So this is going to be -8, -32, a 20, and a 0. And then we're supposed to add what we get when we do scalar multiplication with a 2 on the outside and then whatever matrix B is on the inside. So this is going to be 2 times -3, so that's -6. 2 times 8 is 16. 2 times 6 is 12. And 2 times -5 is -10. Now, we are not done with this until we actually go through and add these element by element. Now remember, it was a 2 by 2 to begin with. That was a 2 by 2 to begin with. So our end result, our resultant is going to be a 2 by 2, and we're going to go through and we're going to add these element by element. So -8 minus 6, -14, -32 plus 16, that's going to be -16, 20 and 12, that's going to be 32, and 0 and -10, so that's going to be -10. So that right there, that's the answer. Now, this next one looks really ugly. So if I were to distribute this through, this is going to be, let's see, 2/3 times 1, that would be 2/3. This is going to be 4/3. Let's see, that one's going to be 8/3, and this one's going to be 10/3. And then we've got to figure out what this is when we distribute through. But remember, it's always important to check the dimensions. This is a 2 by 2, and this is a 2 by 3, 2 rows, 3 columns. There's no way that we can do those. So this is going to be not possible. Thank heavens, right? Because we're going to get some really ugly fractions on that. Okay, let's take a look at this next one. This one says we want to do 4a minus 6b. Again, we could go through and we could multiply a 4 in here and multiply a 6 in here and then do a little subtraction problem with these. But remember, this is a 2 by 2 and this is 2 rows and 1 column, so that's a 2 by 1. So this is also going to be not possible. It really pays to check those dimensions before you start plowing through and trying to do the problem. So let's take a look at this example right here. It says solve the equation, and this is kind of interesting, so I want you to take a look at this. If these were just plain old numbers, so if this was a plus 5 equals 7 or something like that, we would know what to do here. We would subtract the 5 from both sides, so we'd solve the equation, get the variable on one side by itself. Well, with this one, we've got a matrix here. A capital letter is going to represent a matrix, and we want to get rid of this matrix right here. So we know how to do matrix arithmetic. We are going to subtract this one from this side. So this is a -3 and then a 6. So if I subtracted element by element, this is going to be 7 minus 7. That's going to be a 0. This is going to be a -1 minus a -1, so that's going to be a 0. So those are going to cancel each other out. They're going to make the identity matrix a 0 matrix. So on this side, we're going to have an A, and then over on this side, here's where we've got to go through and actually do the arithmetic. So we're going to be subtracting 7, -1, -3, 6. So here's what we end up with. Remember, this is a 2 by 2, and this is a 2 by 2. So we get a 2 by 2, and let's check and see what we've got. We've got 4 minus 7, so that's going to be a -3. We've got 8 minus a -1, so those are going to get, that's going to be a +1, so that's going to be a 9. 5 minus a -3, so that's going to be a +3, so that would give us 8. And then 2 minus 6, that's going to give us -4. That right there is the answer. So we would do exactly the same thing on this other one. So here's what I'm going to do. I'm going to move this matrix to the other side by subtracting. So we're going to subtract this matrix right here, -1, 5, 3, -7. So we get, don't forget this, we've got a -a, and then we end up with, let's check and see, -2 minus -1, so that's going to be a +1, -2 plus 1, so that's -1. 4 minus 5, that's -1. 5 minus 3, that's a 2. 3 minus -7, minus a 7 would be a +7, so that's going to be 3 plus 7, that's going to be a 10. Now we're almost done. We've almost got the a by itself. All we need to do is get rid of that negative there. So let's multiply both sides by -1. So those are going to cancel. We end up with a is equal to, and if you just distribute that through, do scalar multiplication, this is going to be a 1, a 1, a -2, and a -10. Circle that, and there's our answer. Now, this is number 14 on the last assignment. So this is a single, a double, and a suite room. This is a weekend price, and this is a, weekday price, and this is a weekend price. Now, if you need to go back and take a look at that problem, please do. This is one where they gave you some information. They just said, hey, organize this into a matrix. And it says, if the hotel raised all their prices by 10%, what type of matrix arithmetic could help find the new prices? So again, this is a single room, a double room, and a suite. These are the prices during a weekday. These are the prices during a weekend. The company, the hotel, wants to raise all the prices 10%. So what type of matrix arithmetic could help us figure that out? Well, we want all of those to go up 10%. So here's a hint. If you want to find the new prices after 10%, okay, how do you multiply, or what do you multiply by to get a 10% increase? Well, we're going to do 100% of the original price plus 10% increase. So that's going to be 110% of what it was before. So what we're going to multiply by is 1.1. So we're going to do 1.1 times every single one of these. So this was $60, $70, $75, $79, $89, and $95. Now, if you want to grab your calculator and do that, that would be totally okay. I'm going to go ahead and do that. So I'm going to pull up a calculator. Now, I'm going to save this for the ones that I need because I think I know a couple of these, because 10% is pretty easy to calculate. 10%, we just move the decimal over one place, so that would be $6. So this is going to be $66 here. This is going to be $77 here, and this is going to be another $7.50 on top of that. That's going to be $82.50. Now, I'm just going to go through and double check that one right there. So 1.1 times 7.5. There's our, times 75. Yeah, so that would move the decimal over. 1.1 times 75. Sorry about that. 82.50. There we go. So let me do each one of those. So this is going to be, clear this off, 1.1 times 79. 1.1 times 89, and 1.1 times 95. Okay, so we've got 8690. So 8690, 9790, 9790, and the last one was $104.50. So 104.50, and that right there would be the answer. So scalar multiplication would be the answer. So this is going to be scalar multiplication is what we would do to help take care of that. All right. I do have a thought experiment for you. I'm going to slide down here and take a look at this last one. And the question here is, can you think of why they came up with the word scalar to describe this type of multiplication? Why do they talk about this in terms of a scalar? Now, in 7th and 8th grade and previous classes, you've probably run into something called scale factors or proportionality or different things like that. When we scale something, we make it bigger by the same factor, or we make it smaller by the same factor. We multiply it by the same number to make it bigger or smaller. Numbers bigger than 1, scale it up, they make it bigger. Numbers smaller than 1, scale it down, they make it smaller. So scalar is like a scale factor when we do scale drawings and that sort of thing. So go ahead and fill out the little self-assessment here. Take a look at the assignment, and good luck with that.